Edexcel Further Maths Core Pure 1 Specimen Paper Question 1. It should be pretty clear from a quick glance that this question involves hyperbolic functions, and the first thing you might be thinking is, what are the definitions of the hyperbolic functions? So to remind yourself, you know that cosh and sine are both defined exclusively in terms of e to the x. So e to the x and e to the minus x. The question is, what's the link between? Because if you're anything like me, you will occasionally forget, is this a plus? Is it a minus? And the quickest way to make sure is to remind yourself that cosh and sine are designed to be comparable in some way to sine and cos. So cosh mimics cos in many ways, and sine mimics sine in many ways. And the most basic and fundamental way that they mimic one another is that cosh of 0 is the same as cos of 0. In other words, it gives an answer of 1. Which means that if we try putting in 0 here, e to the 0 plus e to the 0 or e to the 0 minus e to the 0, only one of those is going to give the answer we want. So we know that cosh of x is equal to this, and sine of x is the other one. That's going to be e to the x minus e to the minus x over 2. However, although that is a good starting point and it's useful to have that in the forefront of your mind when you're dealing with things like this, it's not, strictly speaking, essential. Particularly for a question like this, you might find there is a much better way of solving it. So we're going to look at the most efficient way first, but then if you want to continue and watch the alternative, perhaps you've had a go at it and you got bogged down with the using e to the x to solve the problem, we'll see how well that can work. So the first thing to notice is that we need the formula book, or we'll find the formula book useful. This is the further maths section of the formula book, and if you scroll past the first couple of pages, you will find the section on hyperbolic functions. There's a whole section here. It gives a few identities, and it also gives the definitions in terms of logs for the inverse hyperbolic functions, r cosh, r sine, and r tanh. So if we make use of that, we're going to find that quite helpful. The first thing to notice here for this equation, think back to your A-level maths course. If you've got an equation involving, let's say, cos of 2x and sine of x, the first consideration should be, how can I turn both of those into just cos or sine of x? In theory, both of them in terms of 2x will be just as good, but it's going to be easier to convert a cos of 2x to cos of x and sine of x. And similarly, for hyperbolics, we're going to find it easiest to convert that cosh of 2x into something involving cosh of x and sine of x. So what do? Well, luckily that one is provided for us in the formula book. Cosh of 2x is equal to cosh squared x plus sine squared x. It might feel backwards, but remember Osborne's rule says that if you've got the product of two sines, you change the sign. So whereas cos 2x is cos squared x minus sine squared x, cosh 2x is cosh squared x plus sine squared x. And that on its own is helpful, but it's not the end of the world. It's not the finished product, because we have cosh squared and sine squared, as well as sine and a number. So it's not quite in its final form. And the thing that's causing us a problem here is not the fact that we've got x's and two x's, we've dealt with that. It's that we have a cosh as well as sine appearing. Sine and sine squared, they don't necessarily cause a problem on their own, because if you think about it, this is almost a disguised quadratic now. The only thing causing a bit of an issue here, the spanner in the works, is the cosh squared x. But again, these identities come to our aid, so we can rewrite this and change cosh squared into 1 plus sine squared. Remember again, the change in sign. That's why it's helpful to keep one page open if you've got your formula book handy to check up on this, so that you don't need to be second guessing yourself when it comes to changing the sign of the sines. What we have here now simplifies to 12 sine squared x plus 4 sine x minus 1 equals 0. And in that form, it should be really quick and easy to see we're dealing with something that the calculator will let us do, solving a quadratic. We put in 12, 4, and minus 1, and we get our solutions of 1 over 6 and minus a half. Make sure you get the signs right on these as well. It's easy to mess up. If in doubt, click back through, press equals a couple more times, get back to here, make sure the numbers you've got here match the numbers you've got here. It's an easy mistake to make, and all of us will do it at some point. So we have not x equals, because remember, although we put it in as if it was a quadratic involving x, we know it's a quadratic in sin x. So sin x equals a sixth, or sin x equals minus a half. But we're not finished yet because they've asked for the solutions to the equation. In other words, we need to find x. We're solving for x. That's implied within the phrase solve the equation if x is the variable that appears. Which means we have a little bit more work to do. But fortunately, these last three identities come in handy here. These come directly from what happens if you try solving an equation involving one of these things. When you multiply through by e to the x, you can end up turning that into a disguised quadratic in its own right. And you can solve for e to the x and then take logs to solve for x. And that's where these logarithm terms come from. And although it's helpful to be able to do that, we don't need to perform that process this time around. We can just use the fact that if x is equal to inverse sine of a sixth, we can substitute directly into the formula for inverse sine. We'll have ln of a sixth plus square root of 6 squared plus 1, which you can either do, you can either simplify this by hand or you can let the calculator help you out. Remember, the calculator is pretty good at dealing with most combinations of surds, so allow it to help you by simplifying things like this for you, perhaps a little more quickly than you otherwise could. Unless you delete everything along the way. 1 over 6 plus the square root of 1 over 36 plus 1, and 1 plus root 37 all over 6. Remember, what I've put in here in the calculator is not the value of x, it's the value of the stuff inside the log. I'm very conscious that if I try doing log of all of that stuff, I'll just get a messy decimal that doesn't help me much. And it does say here, give your answer as an exact logarithm. So my answer here should be ln of 1 plus root 37 all over 6. And that's my answer. Now, if you are a little concerned that you are expecting more answers, well, in a sense you are. We'll get more from this branch. But just to remind you about how the sine function works, if you sketch sine, you'll realize that although it does bear some similarities to the sine function, it crosses at the origin, it has a gradient of 1 at the origin, it is not a periodic function. It's not like sin x, which does this. It doesn't repeat over and over again. In fact, based on the definitions of sine, it's a combination of e to the x and e to the minus x. More precisely, because it's e to the x take away e to the minus x, it's a bit like the average of these two functions. There's e to the x at the top, and sin x will look more and more like e to the x as x gets larger positive, but it'll look more and more like e to the minus x as x becomes a larger negative value. You can see that the further you zoom out, the closer the graphs become. That means we're not dealing with a periodic function. We're dealing with a well-behaved one-to-one function. We can substitute any value in for x and we'll get a single unique value for y, and vice versa. We can reverse this perfectly. So if we were to put in, for instance, ln of x plus the square root of x squared plus 1, this is defined everywhere. This function is defined everywhere because if you square a number, whether it's positive or negative or 0, you'll get a number that's non-negative. When you add 1, you get a number that's definitely non-negative. So it's going to be positive, strictly positive. You can square root that, you can add any number you like. And because x squared plus 1 will always have a square root which is larger than x, even if x is a negative number, we'll still be doing ln of a positive value. And that's why this is defined for all values. You can see that this curve, if I get rid of the e to the x's, this curve is the perfect inverse of this one, which is what you would expect. They are reflections in the line y equals x. So this is the only solution for sin x equals a sixth, and we can do something very similar for the next one. So we want inverse sine of minus a half. We've got to be a little careful with our negatives here. First time I worked through this question, I missed my minus and it gave me answers that didn't work. I'll show you how I found it before it was too late in just a moment. The square root of minus a half squared is still a quarter, so this should work itself out fairly well again. Ln of, we have minus a half, and then we have plus the square root of, and that's going to be 1 quarter plus 4 quarters, so 5 over 4. The nicest way to write this is root 5 over 2, and then of course you can bring in the minus 1 over 2 to make it minus 1 plus root 5 all over 2, and that gives us our second solution. Now, if you rush through a question like this because you're feeling fairly confident and you think you've got it right, that's great, but it's always worth having a check method. Do you have a method you can use that will help you check these answers? And probably the quickest, anytime you're solving an equation, is to make use of the table mode. That is menu option number 9 on the calculator. If you look down here, table mode, this will allow you to put in 2 different functions if you need to. We only really need one function here. We're going to do 6 times cosh. Remember, you need the option button for this. Choose the hyperbolic, and we'll do number 2, cosh of 2x, and then close brackets, plus 4 lots of option hyperbolic sine of x, close brackets. And you could put a minus 7 in here if you like, so that you're trying to find zeros, another word for roots, or you can just leave it like this and know that you're expecting to get 7s. Another thing you can do is put the right hand side of your equation in here. This one, it's not really worth it, but if you had something more complicated, it's useful to know you can put in those 2 functions. And then our table range doesn't really matter what values you put in here, but you can see the right hand side of the equation will always be 7, the left hand side will be all sorts of various things. What I'm particularly interested in checking are these values. So it's a bit of a hassle, but you can type in ln of 1 plus root 37 over 6, close brackets, and check that f of x and g of x both give the same thing. That tells you that what you've substituted in is, at least to how many decimal places the calculator can evaluate it, it is to all intents and purposes giving the same thing for the left and right hand sides of your equation. We can check the next one. This is minus 1 plus root 5 all divided by 2. And that one also works. That value gives 7 for the left and right hand sides, correct to whatever the calculator can do. So it doesn't prove they are solutions, but it does prove that they're very, very close, even if they're not, because the calculator believes they're solutions. So I can move on from this question feeling confident that I've got the correct answers. Now, I said that I would show you the best method first. I'll also show you what happens if you attempt to use the fundamental definitions. Now, technically, you could use the definitions to derive these identities and then use the identities, but I'm going to show what happens if you attempt to use them